All right, today we are diving into something that sounds like it was ripped straight out of a sci-fi movie, but I promise you, it's happening in real labs right now. We're not talking about theories on a blackboard anymore. We're talking about a proven experimental link between quantum computers and actual traversable wormholes. So picture this. You're a top physicist, you're working on a project that is so out there, it almost feels unreal. And then the data comes in, and it's so profound, so reality-bending, that the only words you can find are, "I was shaken." That was the real, actual reaction of Dr. Maria Spirapoulou back in late 2022, the moment her team got the first confirmation that they had successfully passed a signal through a wormhole they created. So yeah, that's the big question, isn't it? A wormhole, not on paper, not in a Hollywood special effect, but inside a physical piece of hardware. How on earth did they pull that off? And what does it mean for everything? Let's get right into it. And look, this wasn't some fringe experiment cooked up in a garage. We're talking about a landmark paper published in Nature, one of the most respected science journals in the world. And the team? It was a collaboration between the absolute heavyweights, Google's Quantum AI Lab, Stanford, and Princeton. So here's the nuts and bolts of what they did. Using just 9 of their quantum bits, their qubits, on their Sycamore processor, they managed to send quantum information through a wormhole. Now, that fourth bullet point, confirming the ER equals EPR conjecture, that's the real bombshell here. It's the first time anyone has ever experimentally proven that quantum entanglement, that spooky action at a distance, is literally the same thing as the geometry of spacetime. But as you can see at the bottom, there was a catch. To do it, they needed a very special, very stable pulse of negative energy, and that stuff is notoriously hard to make. Which, of course, leads to the next big question. Quantum computers are, well, they're delicate, incredibly fragile. So how did they manage to create an environment stable enough to host something as wild as a wormhole? The answer, it turns out, was hiding in plain sight, in another major breakthrough they'd made just 1 year before. And that secret ingredient is one of the weirdest, most wonderful, most mind-bending concepts in all of modern physics, the time crystal. You see, the very same team at Google had already created the world's first true time crystal back in 2021. And this wasn't just some unrelated side project. It was the key. So what in the world is a time crystal? Okay, you know how a regular crystal, like a diamond or snowflake, has a pattern that repeats in space? Well, a time crystal has a pattern that repeats in time. It's a brand new phase of matter that flips back and forth between two states forever, without using any energy. Think of it like this. It's a perfect clock that just runs, forever, no batteries needed. It's found this bizarre loophole in the laws of physics as we know them. And here's its signature move. This is how you know you've got one. If you poke it with a laser at a certain frequency, let's say 7.83 times a second, it doesn't respond at that same frequency. It pushes back at exactly half that speed, every single time. This behavior, called period doubling, is the undeniable proof. It's the smoking gun. Okay, so we've got the time crystal in 2021 and the wormhole in 2022. Same team, same machine. Now we're going to connect these dots, and this is where your brain is going to start to melt a little bit. It's fantastic. Now, the easy assumption to make here, and what pretty much everyone thought at first, is that they used the time crystal as the tool, right? That they basically built a time crystal to act as a stabilizer, to generate that negative energy and hold the wormhole open so they could run the experiment. Makes perfect sense. But that's not what happened. Not even close. The reality is so much bigger, so much weirder. They didn't use a time crystal to stabilize the wormhole. Get this. The wormhole throat, at the most fundamental level of its physics, is a time crystal. They are the same object. And they had the receipts to prove it. When they analyzed the data from the wormhole, it ticked every single box that defines a time crystal. It oscillated. It had that perfect half-frequency period doubling. It was stable. It didn't lose energy. It even had this weird property called many-body localization, which is basically a quantum superpower that keeps it from just falling apart into chaos. It was a perfect match. Not an analogy, an identity. Okay, so let's just pause and absorb that. If a wormhole is a time crystal at the quantum level, well, the next question is obvious, isn't it? Can we build a big one? Can we scale this up from the quantum realm to our world? And this amazing discovery has led to two main ideas for how we could actually engineer this. You can think of it like a vehicle versus a doorway. The first design is a ship, which would create a time crystal around itself, a warp bubble, to travel faster than light. The second is a portal, a stationary wormhole connecting 2 points where the time crystal is the bridge you travel through. So let's just look at the ship concept for a second. This isn't just wishful thinking, there are actual engineering principles behind it. You've got a plasma chamber, a whole bunch of radio emitters, and these really cool things called Casimir cavities. Those are the key to generating that weird negative energy stuff we need. The whole idea is to get all these parts working together in resonance to form one giant, ship-sized time crystal, and the result would be a stable warp bubble that the ship sits inside. All right, I can hear you through the screen. A starship? We just went from 9 tiny quantum bits to a full-on starship. That's a huge leap, and you're right to be skeptical. So let's ask the question, is this actually for real? And the honest answer is, we don't know for sure, yet. But, and this is the important part, there's a plan. A real, scientific, testable roadmap to find out. This isn't about blind faith, it's about doing the experiments. And you gotta love how they've laid this out. It's so smart and cautious. Step 1 isn't build a starship, it's test one single component. Build one Casimir cavity and see if it has that time crystal signature. If it does, great, you move to step 2, a small-scale prototype. Only if that works do you even think about building the full thing. If any step fails, you stop. You don't waste billions of dollars building something based on flawed physics. And this brings a healthy dose of reality to the whole thing. The scientists are being totally upfront about the odds. Right now, based on just the theory, they're giving it maybe a 15 to 30% chance of working. But look how that number grows. If they can get that first component test to work, the confidence jumps to nearly 50-50. If the small prototype works, you're looking at a 60 to 75% chance. This is science in action. You chip away at the I don't know with actual experiments. You know, maybe the most powerful piece of evidence here isn't any one experiment or any single design. It's the convergence. It's the fact that you have quantum computing guys at Google, plasma physicists, and even theoretical physicists all starting from different places and all arriving at the exact same answer. It's like different teams of climbers starting on opposite sides of a mountain with no contact, and they all end up at the exact same peak. That tells you the peak is real. So let's just end on this thought, which is bigger than just engineering or spaceships. What Google proved is that space-time can be made to crystallize, to form a stable repeating pattern in time. So if the very fabric of reality can do that, what does that say about time itself? Is it just the flowing river we've always thought it was? Or is time something else entirely? Something more like a crystal, something solid, tangible, and maybe, just maybe, something we can learn to build with?